Good afternoon, everyone. So we'll continue with the applied optic courses on this online lecture series. And now in the second section, what we will be covering is more about LEDs, basic principles of LEDs, characteristics and application of various kind of LEDs. Then we'll jump into lasers. Some of the acknowledgements of the books that are recommended to study. A lot of these parts have been covered by SMZ and senior activity. Now, let's try to understand that we don't really see the whole spectrum of the light. So, if you consider the whole spectrum of electromagnetic radiation, then there is only this much, which is a visible spectrum, which has these seven colors. Now, not everything is uh, like most sensitive to our eyes, and if you consider then with the eye sensitivity, then this is the region which has the highest sensitivity. So when we are building up LEDs, we need to be thinking about these parameters. Now, the effectiveness of lights for stimulating the human eye is driven by the relative eye sensitivity, a luminous, which is strong function of wavelength. The maximum sensitivity of the eye is at 0.555 pm, and the value of this falls nearly zero at the boundaries of the visible spectrum, 0.4 of this microns. So in case of color of the red or violet eye sensitivity is the lower compared to green, and it takes higher intensity to achieve similar brightness as observed by human eyes. So that's the aspect we need to understand for building LEDs. We covered a detailed understanding about recombination process. Now we need to understand some more while studying LEDs, that from valence band and conduction band, from conduction band to valence band, the transition of electrons, they can happen in terms of interband, so from one band to another one, it can transit. The transitions can involve chemical impurities or physical defects. So defect centers can actually work as recombination centers. And there is also intra-band transition. Within the band, you can also have transitions. Now, the optical process for intra-band transitions between a photon and electron in a solid makes LEDs. So if you have like this He, which is a photon coming in, and it's get absorbed, then it goes to the conduction band. Whereas with a spontaneous emission, it gives away this photon also. So that is used for LEDs. It could be stimulated also. So for lasers, we use this stimulated one, this mechanism. And we create this with the help of the incoming photon that stimulates the emission of another similar photon by recombination, giving out the net of two photons which are coherent. The optical process for the interaction between photon and an electron in a solid is also interesting, because either for photon absorption and emission, the conventional theory for optical transition between the conventional, the valence and the conduction band of a direct bandgap material is based on a case selection rule. So some of this I've discussed in the previous class, that for this kind of a transition, we really need to take care of the conservation of momentum. So the wave vector k1 of a valence band wave function and the wave vector k2 of the conduction band
must differ by the wave vector of the photon. Since the wave vector of this electron is much larger than that of the photon, the K selection rule is generally written as K1 is equal to K2. The allowed transitions are then between the initial and final states of the same wave vector and are called direct and vertical transitions. When the conduction band minima are not at the same value of K as the valence band, the existence of the photon is necessary to conserve crystal momentum, and the transition is called indirect. The radiative transition in indirect bandgap materials are much less probable. To encourage light emission in indirect bandgap semiconductors, special type of impurities are induced. The wave function change and the K selection rule does not hold. The modification of bandgap can be done by alloying. That is why we have materials like gallium arsenide phosphide. So they act, so they take care of the theories that we discussed in the last slide.